Hey guys, welcome to lecture number 3 in Calculus 1. So today we will start talking about the limits of functions. And this is chapter number 2, by the way. And we will start, in this lecture, we will only start talking about, I will give you the basic idea of what the limit is. And on Wednesday, we will see how to compute limits of functions. We'll see more algebraic computations of limits of functions. So let me start with the basics to see what a limit of a function is. And we have seen in the first chapter that we have seen that what a function is, what a graph of a function. Also, we have talked about trigonometric functions as well, or inverses of functions. Oh my. You see, this is, all right. See, this is what happens. I have to admit, so I have to interrupt the lecture. Anyway, so today, like I said, we will define the concept of the limit of a function. We would like to see what that is, and let's get started. So let me see, give you the informal definition of the limit. But in fact, let me look at a function. So let's look at this function. Look at it. Is the function x squared minus 4 everything, so over x minus 2. So this is a rational function, right? If you look at it. And of course, can you see something about this function before we even talk about, what can you say about this function when you look at it? So x squared. Yes,
it's
please.
A difference of squares.
On the top, right? So like Kyle says, x squared minus 4 can be factored into x minus 2 times x plus 2, right? And when you divide by x minus 2, you can, this is simply just x plus 2, right? So now if I'm asking you something like this, if x is almost 2, you see, when I say this word almost 2, when you see x is almost 2, so basically it's it approaches 2, but it's not quite equal to 2. So that's why we say x is almost 2. You can say, we can say that, or let me write it here, x approaches the number 2. Well, you see, it's in a neighborhood of that number 2. It's very, very close to the number 2, but it's not equal. So that's what we mean when we say that if x is almost 2, well, x approaches 2. You know, it's like you going to the mall or to the shop, and you say like, I'm approaching the shop, but I'm not quite in there yet, but I'm almost there. So that's exactly what do we mean by this. When x is almost 2, we say x approaches 2. Well, as you can say, when I deal with since this function here is nothing else than just x plus 2, when x is almost 2, then we can say that f of x is at most what? 2 plus 2, which is 4, right? Or you can say as x approaches, let me write it like this, as x approaches 2, it follows that, this implies that f of x approaches 4. Well, approaches 2 plus 2, let me write it in this way, which is 4. Right? Because keep in mind that f of x is nothing else than just x plus 2. Just look at it here, right? And as you can see, sketched on the graph, well, x plus 2 is nothing else than a line, right? And you see the point here, right? All right. So in other words, instead of well, explaining all this in words, we can write it in the following way. So we will use the following notation, as you see here. So the limit as x approaches 2 of f of x equals 4, or we can say that the limit as x approaches 2, this is how we're going to read it, of x squared minus 4 over x minus 2 is 4, right? So let me just write it completely so that you can see it. So I'm going to use the factorization here above. So we can say that. That the limit as x approaches 2 of f of x is nothing else. Keep in mind who f of x is the limit as x approaches 2 of x squared minus 4 over x minus 2. But this guy is nothing else than just the limit as x approaches 2 of x minus 2 times x plus 2, everything over x minus 2, as you have seen the factorization here above. And this guy here will be nothing else, so this guy will be the limit as x approaches 2 of x plus 2, because these two guys here will cancel. And now, as x approaches 2, what do you think? Holy moly. Oh, I forgot about charging the pen. Okay, so as x approaches 2, what do you think x plus 2 will approach? Can you tell me? So it's 2 plus 2, which is 4. Let me write that. And that's the answer. You see, the essential role was played by this factorization here. It was crucial for us. This one here was crucial for our limit. And now let me explain one thing. Before we talk about this factorization, before we even employ this factorization, I want to ask you one thing. Look at the function f of x equals x to the x squared minus 4 over x minus 2. So suppose you don't have this idea with the factorization of x squared minus 4. If you plug in, so if you take x to be almost 2, x squared minus 4 will be almost what? Can you tell me?
0.
Will be almost 0. Will be almost 2 squared minus 4, which is 0. Well, as also, let's look at the bottom, right? So this is the top. So the bottom, as x is almost 2, x minus 2 will be almost what?
0.
0 again, right? So the value of the limit, so this means that as x approaches is almost 2, f of x will be almost what?
Undefined?
Or specific. It's 0 over 0, right?
1.
Wait, no. Once again, look at the top here. So as x approaches, because I want to make sure that you understand, guys, because this is a trick here that, let me stress this again, this is a trick here. But if you don't know this, you're in trouble, because as x approaches 2, and I'm going to write it like this, right? X arrow 2, x squared minus 4 will approach 0. And x minus 2 will also approach 0. So as x approaches 2, or as x is almost 2, f of x will be almost what? Zero over 0, right? And f of x will approach 0. You see the top is 0 over 0, which is undefined. So make sure you see this is what you first this is your first instance of the limit. And then you see that when you have something that is undefined, you need to come up with something, with some magic trick, which, well, I wouldn't call this a magic trick, but this guy, x squared minus 4 over x minus 2, this factorization will play an essential role in finding the limit, right? Is it clear for everybody what I'm saying?
Question.
Yes, please.
So do we only use factorization when we have 0 over 0? That's it.
That's a very good question. Not necessarily. We can use factorization also when we have other undefined limits, such as infinity over infinity. And I will explain as we go along the way, and we'll see the limits. You will see that there are 7 limits that are undefined. You will see that this is one of them. It's 0 over 0. So make sure this is one of them. Let me stress this. So 0 over 0, this guy is undefined. This is important. And also there are others such as infinity over infinity, infinity times 0, 0 to power 0, infinity times 0, and 1 to infinity. And we will see how we will deal with each and every one of them. But so far, what you know is that in this case, when you have 0 over 0, then you need to come up with something. So, right, when you have a limit of a function, you plug in the number that is approaching to you plug in the number for the variable that it approaches to, and then you'll see what, if you get an undefined, then you need to come up with something, just like we have seen in this simple case here. Anyway, so this is the story a bit with the informal definition of limit. And now let me go a bit and say a few things about what I just said earlier. So we're going to read the limit as x approaches this number c of f of x equals L. So keep in mind, this is the limit of f of x as x approaches c is L. So these two are the same. So now if I go back to the previous examples, you see here, you see, the limit as x approaches 2 of f of x is 4. Or you can say that the limit as x approaches 2 of x squared minus 4 over x minus 2 is 4. Well, in our case, f of x is x squared minus 4 over x minus 2. Right? Okay. And you can come up with the other examples. Maybe I'll give some other examples as well so that you can see how we play around with this. But once again, keep in mind that this is the notation of a limit. So this is how we're going to read. The limit as x approaches a number, which is c of f of x equals L. We write it like this: lim as x approaches x arrow c of f of x equals L. And this is how we're going to read it. Okay. I hope this makes sense. And now let me show you some graphs. Look at these two graphs. And let's interpret them a bit. You see, the function, you see the difference between them? You have this point here, x2. Also, it's contained for function. So the moral is that the limits, well, as you can see in both cases, you see the domain for the function f does not contain 0.2, is not there, but for the function g, somewhat, so it will contain the 0.2, which is a good thing. So it will be a piecewise function. So in both cases, we can say that the limit of as x approaches 2 of f will be the same as the limit as x approaches 2 of g of x, right? Which both of them will be 4, as you can see. Like I said, f and g, they differ only by that extension over there at x equals 2. So the point is that the limits only care about tendency. So this is the word you should care about. It's about tendency, right? And what happens when you get 2, it doesn't matter. Do I make myself clear? Right, so that's what you say. When you approach something, you tend to something. So it's a tendency. It's not like the actual value. Of course, when you deal with limits, you're going to plug in the actual value, but make sure that you get it's in your head. It should always be the tendency. So this is how you interpret the limit of a function. Okay. So now let me veer towards informal computation of a limit. And one of the limits that you should know, and in fact, we will kind of prove this. In fact, not kind of, we will actually prove this when we will talk about this very famous procedure of computing limits of functions, which will involve derivatives. And this will be L'Hopital rule. And we will prove this limit. But so far, just keep this in mind because it will be very useful in applications. So the limit, if you take the function sine and you divide the sine of x and you divide it by x, right? This limit as x, when x is small enough, so in other words, as x approaches 0, will be 1. This is important. This is 1. Right? And if you look at the graph, just look at the graph. You see, the value 1 is there, right? And if you look at the graph, it will, the tendency when x approaches 0, it will go to 1. It's quite clear. You see, it goes down, up. It's like basically a mountain. And then it goes down, right? So you can see this from the graph of the function. So that's the graph of sine of x over x. All right, but in any case, you should remember this. This will be a very useful limit, and we will see many examples next time when on Wednesday, when we will actually use this and some other limits of this kind. Okay. Now, let me give you an informal computation of the limit. And look at this. The limit as x approaches -2 of, you see on the top we have x squared, we have a quadratic function, quadratic polynomial, right? So we have x squared plus x minus 2. And on the bottom, we have x plus 2. And we say that as x approaches -2, this is -3. Why is that? Can you tell me? Why do we get a -3? So suppose you don't know the answer here. So it's okay, just like, imagine that this, no, I should put a question mark there. What would you do to this limit?
You could plug in something really close to -2.
You can plug in, you see, that's the thing. in your mind should be always that x is almost -2, but you can actually plug in -2. Let's do this. And if you plug -2, what do we get? So let me put it here. Oops. So in your mind, okay, let's not go that far. Yeah, Muhammad, yes, you can do that. But in your mind, let's do it intuitively first. In your mind, x is almost -2, but you can actually plug in x equals -2. So you can do that. But in your mind is that x is almost -2. So if we plug in x equals -2, what do we get? So we get -2 squared, which will be 4. 4 minus 2, what do we get? Will be 2.
2.
We'll get 0. And on the bottom, what do we get?
0.
0. And what is this? 0 over 0, right? Which is undefined again. This is not good. So we get 0 over 0 again. And we don't like that. Ugh. So maybe I should do something which will be pretty similar to what we did earlier, right? So maybe we should
factor it.
Factor, right? We can factor x squared plus x minus 2. How can we factor this?
You can do x.
But wait, hold your thought just a second. Let's do it intuitively. Let's not factor it yet. Let's plug in some values, and let me show you some numerical values first, and then we'll see how we're gonna do this. Look, you see, when x is, let's say, I want to take values. I want to plug in values which are very in a neighborhood of -2, so very close to -2 from coming from both left and right from the. So you see, if I look from the left, if I take, for example, x equals -2.3, then I'll get f of x will be a -3.3. And if I take x to be -2.1, then I'll get f of x will be something like -3.1. So I'm actually plugging in values. And you see, when I'm doing the same thing for -2.05, so I'm very, very close to -2 at this point. I'll get f of x to be -3.5, -3.05, sorry. And also when I plug in -2.001, I'll get -3.001. Wow, very, very close. So, and also when I plug in x equals -2, as we have seen, this is undefined, right? So it's actually 0 over 0. That's what it is. Anyway, let me write it like this. Oh, parentheses. 0 over 0. But by plugging in, for example, now let's plug in some numbers on the right side of -2. For example, if we plug in -1.9997, you'll get -2.9997. You see, again, very close to 3, to -3. And also, when I take x to be -1.9995, then I'll get f of x to be -2.995. Again, very, very close to a -3. So in this way, you will get the impression, you'll have a good hunch that the actual limit is -3. You see, by just plugging in some values. Of course, it's not a proof, but at least you have an idea of what the value of the limit is. Okay, And now, how would we actually compute this limit? So let's see some rigor now. So somebody said, Cameron said, right?
Yeah, you separate it out factor and it'll be x minus 1 and then x plus 2, and then you cancel and then it's just x.
Exactly. So the main idea is to get rid of the x plus 2 on the bottom, right? So we can factor again. We can factor. So we can factor x squared plus x minus 2 as what? As x plus 2 times what? X minus 1, right? And once we do this, and this will give us what? So this will give us that the lim as x approaches -2 of x squared plus x minus 2. Okay, I'm just going to write it directly. And here, let me put it like this so that you can see over x plus 2. This will just cancel, and this would be x minus 1. All right, so this will be nothing else than just the lim as x approaches -2 of x minus 1. And keep in mind that x approaches -2, so this would be -2, -1, or be -3, which is exactly the value that we wanted, right? As you can obviously see here, right? So it's the same idea as in the previous example. And so again, keep in mind that this is what you do first. You plug it in, and you want to see if what happens when you plug in directly x equals -2. You will see that this is undefined. And once you see that this is undefined, then you will say like, okay, then clearly I have to do something else so that I can get rid of that indefinite thing, right? Which is in our case is 0 over 0. All right, so this was another example. Let me talk about one-sided limits. And this will be important. Because in the previous example here, in fact, I would like to go back. You see, we went from the left of -2. So basically values which are less than -2, right? This is what we say when we say we went on the left. Basically with values which are less than -2. And then when we say to the right, we refer to the values which are greater than -2. And this will play an important role when we will define what we call the one-sided limits. And I would like you to, well, I see a question here. Not always, no. It can be the case that you will get different values, but also you can get the same value, and that will have a property. We will talk about this at some point in this chapter. But so basically, yeah, Brian, you anticipated when we'll talk about what we will call continuity. So when these left-hand limit and right-hand limit are equal, and moreover, they're equal to the value of the function at that point, the point C. So when all these three agree, then we will say that the function is actually continuous at C. But anyway, we'll get there. I don't want to jump already. So now let me define what are these one-sided limits. The right-hand limit is when x approaches C from the right. And also the left-hand limit is when x approaches C from the left. And we're going to write them in this way. As you can see, is the lim as x approaches C plus. So when I say x approaches c plus, I'm going to write it here, x approaches c plus. When I say this, this is equivalent with saying that x approaches c and x is greater than c, for values which are greater than c. So from the right. And also, we can also say that, so this is that x approaches c minus, right? This is equivalent with saying that x approaches c again, but for values x less than c. So that's what we mean the right-hand limit and the left-hand limit, right? And now, if you want to go back here, you see, if I want to go back to the previous example, you will see that this is illustrated perfectly. When I say the right-hand limit, I will talk about the values which are greater than -2. In other words, in the previous example, I'll talk about values such as 1.9997 or -1.995. And when I talk about the left-hand limit, right, I'll talk about the values which are less than -2, which are -2.3, -2.1, -2.05, or -2.001, right? So that's what we mean. So keep these in mind, because at some point we'll compute this right-hand limit, so, and also the left-hand limit. You see exactly what do we mean by this. All right. And now let me talk about the one-sided limit theorem. And the theorem says the following. The two-sided limits exist if and only if both one-sided limits exist. So, right, the two-sided limits, so in other words, you see this is the two-sided limit. So here, this is the two-sided limit. Right? So this guy exists if and only if the both one-sided limits exist and they're equal. So both of them are L, and this L cannot be plus minus infinity, otherwise it doesn't exist. So this is very important. Both one-sided limits exist and they're equal. So keep that in mind. If, moreover, these two agree with the value, then we'll say the function is even more, it's actually continuous. But for the limit of the function to exist, then both one-sided limit have to agree. In other words, they must exist and must be equal. This doesn't happen for any function. There are functions for which the limit of a point does not exist, and we'll see examples. Or both of them exist and they're not equal. So, in other words, the two-sided limit does not exist, right? Okay. So keep this in mind. This is a very important observation I want to point out. All right. Now, let me show you some graphical examples. Look at this. In fact, I shouldn't have said it. So look at this function. You see how the function is like. You have it look at the graph. And we would like to find the limit as x approaches 2. You see the number 2 is right here. Look at the number is right here. And we'd like to see what kind of value, where is this? So as x approaches 2, this will be where? So that this is the where is this? This is what I'm interested in. Is it here? Is it there, or maybe it's here? So what do you think? What can you say about the limit for the values less than 2? When x is less than 2, f of
It
x will,
approaches 4.
you see, it approaches 4 for x less than 2. You see it's here. Okay, let me put it like this. You see it goes for values less than 2. So on the left side of 2, you'll see the graph of the function looks like that parabola over there, whatever it is, right? So the limit is kind of 4 if you look at the graph. But for values greater than 2, the limit is what? This number here, so this is 4 here. And this is 3 here, right? The limit will be 3, correct? But these two are not equal, right? If we go back to the theorem, what did the theorem say? It said that the two-side limits exist if and only if both of one-sided limit exists. Well, in our case, look at them, they exist, both of them. But moreover, it says we need something even more, and we need what? We need that those two are also equal. But in our case, they're not equal. You see, they're different. So the conclusion is clear. The limit of as x approaches 2 of f of x does not exist. Is the example clear for everybody? Is it clear for everybody? Does it make sense? Okay. You see, both one-sided limits exist, but the both-sided limit does not exist because those two limits, although they have finite value, but they're not equal. As you can see, 4 is not equal to 3. So the both-sided limit of f of x does not exist. Okay. All right, now let me show you something. Look at this again, something similar. You see, we have the function f of x equals 1 over x, and we have, as we have seen, in the first lecture, the graph of f of x equals 1 over x looks like this, right? So what can you say that when about the limits of f when x approaches 0 from the left, and what can you say about the same thing when x approaches 0 from the right? Well, look, by just looking at the graph, just look at the graph. So when x approaches 0 from the left, for values less than 0, right? Look, it goes down, the graph goes down. You see the value, so I'm approaching 0 as much as I can. You see, I'm approaching 0, but at some point it will go down. So the graph, the limit will be negative infinity. It goes down to negative, right? Right, coming from, but now if I'm approaching positive value, see, the graph will rise. You see, it goes to positive infinity, it goes up. So it will be positive infinity. Of course, these two, both limits exist, but these are not equal. So the limit, so both one-sided limits exist, right? As you can see, one of them is negative infinity, the other one is positive infinity, but they're not equal. So the limit does not exist. Again, I'll go back to, look here, look at the definition, what it says. Look at the one-sided limit theorem.
So can it also not be both because it's working with infinity?
No, you see, if both of them would have been in plus infinity, right? Positive infinity, let's say, then the limit would have existed. Because they look at the theorem. They agree, it's L. Ah, wait. No. The limit, okay, let's not confuse ourselves. Look at L. L cannot be plus minus infinity. You see? It has to be a finite value. So yeah, your observation is good. So because of L is infinity at one of them, then it's over. You see?
Sorry, what was his question?
So his question was, the limit does not exist because it's they're infinity. One of them is actually infinity. And you don't even need to check that these two are equal. Even if these two are equal, then you can say that. You see, the one-sided limit theorem says that L has to be different than plus minus infinity. Well, it's actually, it's kind of restricted. Maybe it's unfortunate, very unfortunate. The statement is kind of unfortunate because I like to avoid the values with infinity. And there will be a special topic for that later on. So that's why it's kind of restrictive. So it's not in its full generality. But anyway, so far, just keep it like this. All right. Now, let me give you another example. And yes, exactly. Yes. Look at this function. F of x equals sine of x. Well, you'll see something. There is something to talk about in this function. You see, it oscillates a lot. So as x approaches, the origin, as x approaches 0, this function oscillates like crazy. And this will oscillate between -1 and 1 as x approaches 0. So it goes up, down, up, down, up, down, up, down. So there is no value which it doesn't go around any other value. It goes all the way from -1 to 1, -1 to 1, -1 to 1, and so on. So the limit, we can say that the limit, in fact, this is a very important thing to say, the limit as x approaches 0 of sine of 1 over x does not exist. This is important for you to know. So the limit of this guy does not exist. Well, this is the intuitive explanation, but in fact, a more formal explanation would be that, when we have usually it's not taught in calculus 1, and it's not explained why. It's only by just looking at the graph because of the oscillation. Well, it's a good reason, but it's not quite actually a proof. It basically says that the function sine is a periodic function, and as x approaches 0, 1 over x will approach infinity, whatever. Depends on how you look at it. From the left-hand side, on the right-hand side, is negative or positive infinity. And there is this theorem which says that a periodic function does not have limit at plus minus infinity unless the function is constant, but this is not the case. So therefore, the limit does not exist. But anyway, that's a little bit more in depth. I wouldn't go crazy about this now. This would be more when you take a kind of a proof class. This is a good prototype to see why the function of a limit does not exist. But graphically, if you look at it, it oscillates like crazy. But you can also say something else about this function. You can definitely say that since it oscillates, well, it's already said it's between -1 and 1. So as x approaches 0. So this is important. So definitely we can say that sine of 1 over x is in absolute value. Let me put it like this, is less than 1. So we can say it's bounded, if you want to, which will be important, for example. As we will see that when we want to deal with the limit of something that goes to 0, but when we want to deal with the limit of some of the product of two functions, and one of them goes to 0, the other one is bounded, then the product will go to 0. For example, the question for you, and I will leave it, what is the limit as x approaches? So we have seen that the limit as x approaches sine of 1 over x, as x approaches 0 of sine of 1 over x does not exist. But now here comes the question, what is the limit as x approaches 0 of x times sine of 1 over x? What's your intuition here? Yes.
Would it be 0?
It would be probably 0, right? I don't know. I'll let you think about this. But this is what your intuition would say, right? Because you can neglect sine of, based on what we said, right? Sine of 1 over x will be, since it oscillates, it's between -1 and 1. So you can bound this by a constant, well, in this case, -1. And when you bound this, when you take the absolute value of x times sine of 1 over x, this will be less than 1 times the absolute value of x, which is 0. But anyway, we need to employ other stuff as well, which we will learn later on, maybe in the future lectures.
Because didn't you say when you restrict the domain that it can be like, it'll work better that way, basically?
Well, what I've said is, what you mean for trigonometric functions, right, Cameron? So in this case, the domain, you can define sine of x. You can define it on R, and the values will be -1, 1. But what are you referring to is, when I restrict my trigonometric functions to a certain domain, I want to make them look nice. That's the thing. I want to make them, I want them to be 1-to-1 so that I can compute the inverse and so on. So that's what I was talking about last week. All right. Any other questions? So that's basically the story. I would not go too much into other details, especially when we deal with some computational details, because you will see this will be devoted for the next lecture. You will see a bunch of limits of functions. We'll see, I'll show you many techniques on how to compute them. So I wouldn't go further on. So I think I will stop here.